Hello, students. We're going to do a very quick piece through chapter 3.2. Of course, you want to make sure that you are reading through this on your own. Sorry for that disturbance. Let's see here. All right, so a couple pieces. Definitely, this is a Common Core. We get to addition. So notice grade 1, add within 100, including two-digit number and one-digit number, including pieces about relationships, including two-digit numbers that require regrouping. So we're talking about grade 1 here. So those of you who are like, hey, I want to make sure I'm teaching at the lower levels, this is a critical concept, as you can imagine. So let's see here. We have the natural numbers and the whole numbers. Don't forget about those. And we're really talking about adding whole numbers. So we're not going to be dealing with fractions at this point, like 2/3 plus 1/2. We're not at that stage yet. So we're building up to get more comfortable with the concept of addition first. Okay. Now we do call this a binary operation. Binary comes from two, just like we had the binary number system. It had two digits, the 0 and the 1. This was also known as base 2. So we're using binary operation because two numbers create another number. Okay. So most of our operations that we do in math are binary. There are some that are not binary. And so that's an interesting thing that we'll take a look at as we go forward. Let's see here. So a couple different ways we can think about addition. This is called creating a model. The model approach helps students firm it up in their mind. So we take something that's concrete, like hands-on, and we make it something tied into something that's a little bit more abstract. The goal of this is not to say, hey, we did a hands-on, now you can do the rest of it. It's so that a student who is doing the abstract operations has something concrete they can refer back to. It is not a goal to continue using things like base blocks for the rest of their lives. It is a stepping stone so that they have a concrete representation of the abstract concept. All right, so let's take a look. Set model is one way. This is typically what teachers do, right? You have 4 blocks, there's 3 in another one. We combine the two groups. How many objects are in the combined group? And if you're taking a look at that, it will look something like this. Set A and set B. Now, it's very important to make sure that there is no overlap between them. So we need the two sets to be disjoint. If there is overlap, this is what we saw in chapters 2 and 3, then we won't add them together and get 7. We would add them together and then subtract the double counted pieces. So it is true that the number of A plus the number of B is equal to the number in the union. But notice this is a key part. It says let A and B be two disjoint finite sets. All right. So then they say, okay, then they continue on with that. This is really one of the conditions of the definition of addition when using the set model. They have to be disjoint. Okay. Terminology wise, the two things that we're adding together, the A and the B, we call those addends. The result is known as the sum. So the individual pieces, addends. Second piece is the sum. You'll notice we don't have a term for which one came first. We will have a term like that when we do division or subtraction, and that's because we're going to see in a moment, addition is known as being commutative. The order of addition doesn't matter, but the order of subtraction, division, and other operators do matter. So that's why we don't have 3 different terms for this. We only have 2. Okay. They added a now try this. Again, as you're thinking through, you should be able to answer things like now try this. All right, number line. This is known as the measurement model. Okay, we're going to measure something out. So what you can do is, and they actually tell you when the plus sign first appeared and the minus sign. So in a printed book in 1489, pluses and minuses referred to surpluses and deficits in business problems. I remember reading something about this. What they would do is as they were shipping things, okay, so let's just say we had a 50-pound bag of flour, something like that, right? You'd weigh it. They didn't have the precision that we do today. So they would dump in something that feels like about 50 pounds. And then they'd put it on a scale and they'd put on the bag that every bag is 50 pounds. They'd put like a +1, which means it's actually 51 pounds. Or they'd put a -3 being below 50 pounds. That would be 47 pounds. Again, they use this as a way of making things easier. Okay, measurement model, you start at 0. And this is a key part for all of these models. There is some, you have to understand how we start them. You can't start from any place on the number line. So you start at 0, you take the first number and you move in that direction. This direction is +4. And I know we're dealing only with whole numbers now, but I want you to understand if you're teaching kids, you want to be able to tell them it's not just that we do it this way, because when they get to the next couple grade levels, they'll be dealing with things like negative numbers. And a negative number would be, in a sense, moving in the opposite direction. That's often why we refer to 4 and -4 as opposites. Okay, so we move 4 units, then we stop, we take the next number, and we move in the same direction. That's why addition, we kind of think of it as like if you're doing this with a vector or an arrow, then you start where that arrow ended and continue. And that does lead, hey, this would continue. If you wanted to do 4 plus -3, we would go 4 units over, stop at 4. Then we would move 3 units, but in the opposite direction. So we get to 1. So 4 plus -3 is 1, and this model still works just fine. Okay. Let's see here. So here's a student error. I'll let you think about that. Here's a kindergarten Common Core. This is ordering whole numbers. So compare numbers between 1 and 10, trying to figure out which one is bigger, which one is smaller. Okay, and we've already seen a definition of less than that related to set definitions. This one feels a little bit more natural to most people, and so I think you'll probably like this one better. For any whole numbers A and B, A is less than B, which is written with the alligator symbol pointing at the A, or the alligator mouth is eating B, whichever way you want to think about it. If and only if, there's our definition, biconditional, there exists a natural number k such that A plus k equals B. Notice we have a quantifier now. There exists. So that means there has to be at least one number that makes this true, okay? Such that A plus k equals B. And notice there has to exist a natural number. Okay? So A plus 5 gets you to your number, good. If it was A plus 0, that is not less than anymore. That would be the definition of less than or equal to. And if you had less than or equal to, you don't have to say a natural number. You could say there exists a whole number. Okay, so a slight tweak in the definition, and we can get the other one. Instead of less than, we could get less than or equal to. Let's move on. Mastering basic addition facts. Those of you teaching younger grades down the road, these are things you're going to want to know. So the counting on strategy is probably the most common. Counting on strategy says if you want to add 5 plus 3, then you say it verbally. You say 5, that's my starting point, and then you count on. And sometimes a student will even hold up fingers as they're getting used to it to move 3 numbers forward. So 5 and then 6, 7, 8. They hold up 3 fingers, they stop. So therefore 5 plus 3 is 8. 7 plus 4, you would start at 7 and you'd count forward. 8, 9, 10, 11. And I know it seems maybe for some of you very basic, but that's what you're going to be teaching. So this might be a struggle to some students. You might have to kind of get them used to counting first, and then they could use the strategy of counting on. Now, doubles. Doubles is a big one. Not just doubles, doubles plus 1, doubles plus 2. So if you see something like 6 plus 7, you can turn it into 6 plus 6 plus 1. So it's the idea of decomposing a number like 7 into 6 plus 1, because doubles sometimes are quick. Okay, sometimes students can do doubling something quicker than they can counting up, especially if they're going up by 7 or 8 or 9. Making groups of 10, big time. Oh my gosh, this is so cool when you start to see it. If you had something, so if you're making 10s, think about decomposing. And I'm using the language, I'm not borrowing or anything like that. I'm regrouping or decomposing. But if I had something like 7 plus 8, right? I can think of 8 as being 3 plus 5. I just break it down because it is. 8 is 3 plus 5. And then I can make a group of 10, and I end with 10 plus 5, which is much easier for most everyone to do. So use that technique. Oh, and another student could have done, oh, wait a minute, I see that as 7. Oops, let me go back. As 5 plus 2 plus 8. There you could make a different group of 10, but the resulting sum would be exactly the same. Okay. So fantastic tools here as you're teaching students to go forward. Again, we've got some grade 1 Common Core. I recommend you read every one of these. When they put them in, these are Common Core state standards, and this is what you as a teacher are going to have to follow. Okay. Now let's talk about it. We talked about addition. We're going to go ahead and say, let's understand some of the properties of addition. Okay. So they call it 3.1. It's really a property. To me, that's not a theorem, but here we say if A and B are whole numbers, so take any two objects in that set and you add them together, you will get a unique whole number. That means when you add, you're only going to get one result. That's what unique means. And a whole number means it's going to be in the same set you picked from initially. So if we add, we get something in the set. Okay. Now they're going to ask you to do some other piece with closure. So I want you to think about this. If you had a set that looked like this, 1, 2, 3, 4, 5, let's say, and we'll stop there, then to be closed under addition, every addition problem we can think of has to be in the set, right? 1 plus 2, well, that equals 3, and 3 is in the set. Okay, that's good. 2 plus 3, that has to equal 5. Let's check. Oh yeah, 5 is in the set. Okay, that's good. But here's the piece. It has to work. It's an if-then statement. So if you start with two numbers in the set, then you have to end with a number in the set. So it's an if-then. So remember how you prove an if-then wrong? I'll pause for a moment. That's right. You meet the condition and fail the conclusion. So that means you find two numbers that are in the set, but when you add them together, the result is not in the set. Let's take a look. 3 plus 4. Oh, 3 plus 4 is 7. Check. 7 fails, therefore not closed. Not every set is closed under addition. The whole numbers happen to be, but it doesn't mean every set is. They will ask you to do problems like this. Part A, take some even numbers, the set of all two n's, as long as n is a whole number. If you need to, write out what this looks like. 0, 2, 4, 6, 8. Now pick any two of those and add them together. Do I get another even number? Then do that for odd numbers. Then do it for the set 0, 2. And don't forget, it just says these two things have to be in the set. So if you could choose the same number twice, that's fine. 0 plus 0 is 0, and that's in the set. So don't think that one time it works is okay, right? You need every time it works. An if-then statement is an all quantifier, right? All dogs are black means if I am a dog, then I am black. That's what it means. So we have to keep that in mind. Moving forward, page 102, we get a nice school box picture here. Now, this is one with colored chips. This is a very common technique at the elementary levels. What they do is they make 10. They're going to do 4 plus 7. What you'll see is they use what are called 10 counters. And you fill them up with your first number, 7. So there's red 7. You're going to add 4. So put the yellow counters in to show what you're adding. And you can see you made a whole group of 10 with 1 left over. And that is where we get our place value. Okay. So you get to try a few of those. Well, you get to at least look at a few of those, right? We're not teaching elementary math. We're teaching you how to think about and understand elementary math at a deeper level. Okay. Next up is the commutative property. This is the property I spoke of earlier, which said if you have any two whole numbers, then a plus b is equal to b plus a. Okay, you can turn the order around. So the order is irrelevant with addition. It doesn't matter what order you do it in. Okay. They have a set model here. So the set model will be take 5 in the first, 3 in the second, switch, take 3 in the first, 5 in the second, you get the same quantity at the end. Okay. And don't forget, there's another property here. These are all things you should know already, honestly, coming out of the intermediate algebra style class. So if you have 3 numbers, any 3 whole numbers, then you can regroup them. Okay, so the associative properties like your associates, the group of people you hang out with. But if you change your grouping with addition, the sum will not change. And that is not the case with subtraction or division. So these properties are not true for everything. That's why we have to think about them as we go together. Go forward. All right, let's jump down here. So we've got closure, commutative, associative, and here's the next one. This is the identity property, and it says there's a unique whole number, and we call it the additive identity, such that, which means for any whole number you pick, if I add my unique number called 0, I get back to what I started with. And it's forwards and backwards, a plus 0 and 0 plus a. So you can imagine it feels like subtraction would work here when we get to that section, a minus 0, but we also have to have 0 minus a. They have to be the same. Okay, the identity property. So yeah, this is a very special number. 0 is known as the identity element. It's a very special number. The natural numbers don't have it, for example. So there is no identity property of natural numbers because you can't add any of them and keep what you started with. Picture this as your identity. Okay, you as a person. What could I do that won't change your identity? Okay, so this is the idea. When you think of identity, you want to stay the same. You don't want someone stealing your identity. Okay, then they give you a list of properties. They do an example here. If you're using the book, there's a you try this version. I think there are videos here. If not, you can check in the back of the book. That should have the answers. And we get up to addition algorithms in 3 and 4. We find they need to fluently add and subtract within 1,000. And it says fluently. That means quick, efficient, and correct. Okay, fluently add and subtract multi-digit whole numbers. So we have standard algorithms and learning some different algorithms. So what we're going to do is, here's the properties, and they talk about that. That's again from a textbook. And this is a grade 3 textbook where we're learning those properties. All right, let's jump forward using base 10 blocks to develop the standard algorithm. Standard algorithm seems to be that since we may need to regroup, that we should start with the smallest value first. So if we had enough of these little 10 pieces called unit blocks, we would be able to make another rod. So if we took 10 of them, we could trade it in. Okay. So this right here, this is known as the expanded algorithm, sometimes called partial sums. And we'll see that in just a moment. Add the ones, write it down. Add the tens, write them down. Then add the result. Notice the standard algorithm does not have anything different. In this case, it's very quick because you don't need to think of it necessarily as 30 plus 7. You could just think of that as being 37. Okay. If you want to be formal, you want to say, well, how would I really do it? If you want to know how addition is really done, you have to use properties. And this is how you would really do addition. Okay. We've got commutative associative properties. We've got a distributive property. We'll get to that one later, but it's expected that you already know it. And then we've got single digit addition of facts. So here we are. So you can't add ones and tens together. You have to regroup them. So you put all the tens together as a group and then you can combine them. Once you have down the concrete models, that's moving the pieces of 10 blocks or chips around, then you can get into standard algorithms. So the expanded algorithms here, where you add the ones, then add the tens, then combine. The standard algorithm is you add ones and then you regroup. And I know you often would have said carrying. We do not use carrying anymore. We try very hard to break students of that habit because carrying does not tell you how far or what you're doing. What you are doing is taking 10 groups of 1 and combining or regrouping them into one group of 10. That's what the 1 stands for. Up here, it's one group of 10. So we use regroup. I sometimes will say fair trade. I think that's a reasonable piece. Students like hearing fair trade, but really we're just regrouping them because we're taking a grouping of 10 ones and writing it as one group of 10. So hence that's why you'll hear this, the term regrouping. So the concrete model, they spelled concrete wrong. That's funny. I'll have to tell them they got a typo in there. All right, let's take a look. So we add, what do we do? So I have 200, I have, what is this? 186 plus 127. Okay, so you see 8 of these and 6 ones, 1, 2, and 7 of these. So I think of pushing them all together. I find 10 ones and I regroup it into 110. Then I find 10 individual rods, I combine them into one flat, and I'm left with the number 3 flats, 1 rod, and 3 singles. If you're using the traditional algorithm, you would get 6 plus 7 is 13. You'd put a 3 groups of 1. Why am I only writing that down? Because the 10 ones can be regrouped, and that's the regrouping symbol up on top. Similarly, 8 plus 2 is 10 plus 1 is 11. Put 1 down, regroup a 1, and then continue to add down. Here are the place values that are being combined one step at a time. And you can see this is actually very, very similar to what you would have done in algebra. The difference with algebra is since we don't always have base 10, like here we have 10 cubed, 10 squared, 10, and 1, we'd have x cubed, x squared, x, and 1. So the difference you can see is with algebra, this is what you're building on to, elementary teachers, right? You're building them up to the knowledge and language of algebra, is that these are not necessarily like terms. If x was 10, then I could do a little bit of regrouping, but at this stage, I cannot. Okay. All right, let's take a look. Partial sums algorithm. Partial sums is not bad at all. It's very similar to the expanded algorithm. All you do is, typically with partial sums though, and I prefer this one, I start left to right. I think it's easier. It gets me close to the answer with my first step. So that means I start with the 500 plus 700, gives me 1200. I know my answer is going to be pretty close to 1200. If I start with the other side, I get 8 plus 7. That gives me 15. My answer is going to be nowhere close to 15. So again, this is why I prefer left to right, and I think your students will too. If they're trying to do this in their head, left to right means less regrouping and less remembering. Okay, so I'd do the 700 plus 500, I get 1200. Then I do 60 plus 50, which is 110. Personally, if I was doing this mentally, I'd add those together right now, which is 1310. Then I add 8 plus 7, which is 15. 1310 plus another 10 is 1320, and add the 5. You get 1325. Mental math, huge. Absolutely incredible. The next one is lattices. A lattice is a grid structure. And the grid structure that you make, if you can see this, make a box under each one and put a line slashing like a diagonal. And so when you add, what you have is 8 plus 7 is 15. I put the 5 in the low box and a 1 in the top box. So what you get, and I'm going to try to shade this here, is you get place values. Here's your ones right here, okay? Next up is your groups of 10 right here. They kind of go on a diagonal, so your place values look different. Here comes your groups of 100, followed by your groups of 1,000. And if we had any regroupings at the highest level, I'd have groups of 10,000. So there you go, kind of like a rainbow flag. That's the lattice. A lot of students love the lattice. They really do. And there's nothing wrong with the lattice, except you got to draw the box every time, right? You have to draw this huge box. So totally up to you if you like that one. There's nothing stopping you from using it. But again, you want to push yourself a little bit to get out of your comfort zone and feel more comfortable doing addition without that. Okay. 144 plus 37, this is column addition, and they're using the base 10 blocks. So what they do is they create the columns instead of just leaving them floating on the desk, and then you can regroup. So you take 10 and you trade it. You see from this step to the next, I now have one additional 10 block. Okay, so 181 is my total. So you can do column addition one at a time. And what you do is you can add all the columns and then start doing your regroupings. And you do your regroupings one at a time. So I'd get 8 hundreds, 11 tens, and 15 ones. But if I was to write that out, think about that, 8, 1, 1, 1, 5. That's not the answer to this problem. So I'm on the right track in terms of my additions. I just have to be thinking about now I need to make sure that my columns match. So regroup one at a time, and again, start from smallest to biggest. So 15 becomes 5 individual ones and one additional group of 10. And then finally, the 5 just comes down. 12 becomes 2 groups plus 1 that gets trained out. Okay, the opposite change algorithm. Opposite change. Okay, so they used to call this equal addends, and the idea is what I can do is I can, as long as I add 1 and subtract 1, or add 3 and subtract 3, I will get to numbers that are easier to work with. I demonstrated this in class the first day. So this is called opposite change. I'm not a fan of the title because I think it's not, what I'm doing is I'm creating equal addends. So the sum will be the same. As long as the number you add and the number you take away, if they cancel out, you're going to be fine. So what they did here is they added 1 to get to 190 because 190 is easier to work with than 189. But if you add 1, you got to take 1 away from the other number. And again, if you add 10 to 190, you get 200, which is way easier to work with than 190. So if you add 10, you got to take 10 away. So you're balancing. Okay. All right. So here's the opposite change algorithm. You make it easier on yourself. If you notice up here for this student, if they were adding 19, if you added 1 to 19, you'd get 20. 20 is so much easier to work with than 19. But if you add 1 here, you got to take 1 away here. So you'd end up with 32 plus 20. And that's going to be much easier to work with. Okay. And this is grade 2. So this is the Envision Math program. Okay, Scratch algorithm. Personally, I love the Scratch algorithm because it's so fast. It's so much faster and less of a challenge from what you might have had growing up. Let me give you an example here. Okay, let's say I had 237, 186, 491, 645. Right, I'm just putting a ton of numbers down here, right? Because Scratch works great when you have a lot of numbers to work with. 500. 78. Okay, that seems pretty good to me. Okay, so I'm going to add these numbers together. Now what you do is this. You add as you go like you normally would. So I'm going to add all the ones up. Every time I get a number bigger than 10, I scratch the number out and I keep going with the number that is still kind of up in my head, the leftovers. So watch this. 7 plus 6, 13, right? In the old system, you would have said 13 plus 1, 14, 19. Then I'd have to keep all this in my head. But instead, I say 13 and I stop and I say, okay, that's a group of 10 and 3 ones. Now keep going, but just with the 3. 3 plus 1 is 4. 4 plus 5, right? 9. 9 plus 8 is 17. So I write the 7 down at the bottom because that's what remains. I count up my scratches, which is 2 scratches, and I keep going in the next column. 2 plus 3 is 5. 5 plus 8 is 13. 3 plus 9 is 12. So scratch 2. See what I'm doing? 2 plus 4, that's 6. And 6 plus 7 is 13 again. So I write a 3 down here. 1, 2, 3 scratches. Okay, 3 plus 2 is 5. There's 6. There's 10. So I put a 0. 0 plus 6 is 11. So I have 2 scratches coming over and I get 2,137. Okay. So it means you only have to keep single digits in your mind. You don't have to keep the whole thing going. So it's a very cool little system for doing large groups of numbers. I would not use this with just small groups of numbers. This is for multi-digit addition. All right. So understanding addition in bases other than 10, you can make an addition table. You've seen this for base 10, 0 through 9, 0 through 9. If this is base 5, you'll have 0 through 4, but the addition is the same. Let's do one on our own. Maybe let's do base 4. Okay. Let's see here. Yep. So here we go. So if I'm doing base 4, addition, base 4. Okay. So in base 4, I'd have a 0, a 1, a 2, and a 3. And I'd have those going across as well. Okay. So just go one by one. 0 plus 0 is 0. 1 plus 0 is 1. 2 plus 0 is 2. 3 plus 0 is 3. Remember, we're in base 4. Anything bigger than 4 or equal to 4, I got to regroup. Okay, let's keep going. 0 plus 1 here is 1. 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 1 is 4. We're in a different number base. And I'm going to leave the 4 off just so you know I've written it as addition base 4. So I get 1, 0, which is one group of 4 and 0 ones. Okay. Keep going. 0 plus 2 is 2, then 3, then 4, then 5. I know some of you said he just wrote 11, but he said 5. I didn't write 11. I wrote one group of 4 and a 1, which is a 4 plus 1, which is 5, because I don't live in base 10 when I'm visiting Forania or Forville, whatever you want to say. Next up, I get a 3. 3 plus 1 is 4, 5, and 6. I hope that you start to see some of the beauty of addition. there is a symmetry to it, right? Look at this. Lines of the same number, because if I go up one in one and down one in the other, I get the same answer. So take a look at that. Look at this beautiful structure here. All of it sitting right there. Symmetry across the board. So occasionally, like if I was doing this on my own, I might do all the zeros first because adding zero is so quick, right? Then I could go down and do the ones. And what I notice is because it's commutative, this piece matches that piece. So I really don't have that much left to do. And if I remember my diagonals, I'll get everything else for free here, and I'm left with just a couple pieces at the end. It's really not that bad. I think you're going to like it. And if you don't like it, that's too bad. This is all I'm going to put on the next test is different number bases. You're not going to be doing much adding at all in base 10 because you already know how to do that. You already know how to do that. All right, this is the column approach. This is the lattice approach. So the lattice is already built for you. And I'm going to tell you, back in the day, maybe in the, shoot, when was this? Early 1900s, they actually came out with paper that was printed with the lattices on it already so that you didn't have to draw them. So it was quicker for you to do the math because you already had the lattices drawn for you. But we're not there today, so you'd have to redraw them every time. Let's see here. We get into mental computation. And again, this is grade 4. By the time they get to grade 4, they need to assess the reasonableness of answers using mental computation. You'll see adding from the left is the biggest one for me. That's the big one. So others, so breaking up and bridging is different. So breaking up and bridging means add the first number in the tens place, right? But you add it to the whole other number. So instead of getting 90, you're going to get 97. Then bridge that gap by bringing in the other number. Okay. Now they call it trading off, where you add 3 and take away 3, where you balance with the equal addends. But that's, again, a really good trick to use. Very, very good to use here. Okay. All right. What else do we have here? Compatible numbers. Yeah. If you had a list of numbers and a couple of them added up to 10 or 100 very quickly, just pull those numbers out and then see what's left over. Okay, so 130 plus 70, that gives you 200 right on the nose. 50 and 50 is 100. That's 300, and you got a 20 left over. You get 320. Okay. Compatible numbers are really big, though. This is splitting things up, decomposing numbers into something that works really nicely. 25 plus 79, you might not see it. But if I said 25 plus 75, you're used to those numbers. Okay, so that gives you the 100, and you have 4 left over from this one. Okay. Estimating, there's a couple different ways to estimate. You can do a front end where you kind of say, okay, let me just take all of the hundreds places, like 1200, and then you kind of chunk the rest together to maybe get an adjustment. And so adjustment here would be very quickly done. So instead of 23, 38, and 61, you find things that's very close to. 38, 61, that's pretty much 120. So add them together, you get 1320. You can just do front-end estimation. This would be pretty close. If you rounded all of them down, this would be pretty close to 1200. Okay. Now you can group to nice numbers. This is another strategy that's used. I'll let you take a look at this one because this is add with mental math from, what grade is this? Grade 3. Okay. Let's take a look here. If you want to kind of find numbers that are compatible, in something in the 30s and something in the 60s is going to get you around 100. Okay. And then the other numbers, 20 and 30, that's about 50. 49 is about 50, so call it another 100. So the sum is about 200. You find close numbers, numbers that work pretty close. And if you have a group of numbers that are all pretty close to each other, it's pretty quick to actually use a strategy called clustering. And clustering just says, hey, all these numbers are pretty close to blank. Let's just say here, they're all pretty close to 6,000. So I have 5 of them. 6,000 times 5 is 30,000. It's going to be about 30,000. Okay, I know I'm off, right? Estimating, I know I'm off, but I'm getting a value that quick, but close. Okay, rounding. What do I do with rounding? I round typically to the nearest blank number. And so if I want to round to the nearest 1,000, I go to the hundreds place, round up on this one, round down on the next one, I get about 8,000. So rounding techniques, Yeah, you want to be pretty careful with rounding techniques. And the reason is if you say it's the number it's closest to, well, if you had 4724, it's definitely closer to 5,000 than it is to 4,000. Okay, so that's why we call it rounding. All right. But what if you actually had the number 4,500? Where would you round that to? And the truth is, if you go up, you're off by 500. If you go down, you're off by 500. So rounding 4,500, it's right on the nose. It has to be exactly 4,500. You're equally wrong each way. So just understand that if a student wrote down 4,000 or 5,000, there's really no reason why you should mark them wrong for either one of those. Okay, that's a perfectly good rounded number. Traditionally, we would take 4,500 and round it up to 5,000. But that's oftentimes just kind of a way to say, hey, let's just make sure everybody gets the same answer at the end of the day, not a way that relies on the reasoning behind why we round. Okay. All right. Is that about it? There's the number line. Yeah, so they're finding the halfway number and they do the same. So what is this, grade 3? Yeah, back to grade 3. All right, then you jump into the homework assessments and you get a chance to find the solutions, give reasons for steps, and so on. I'm going to leave that to you here. Understand when we get to class, we will be doing addition in different number bases, maybe 5, maybe 8, maybe 7, maybe 6, doesn't matter. Any number base is a fair game. Even base 10, but you won't see a lot of base 10, except maybe some from the classroom type of stuff. That wraps it up for today. Hope you have a great day. Off you go.